Book Nibbles. Big Ideas, Small Bites. Roger Penrose's The Emperor's New Mind is a fascinating exploration of one of the most profound questions in modern science. Can human consciousness ever be fully explained as a computational process? Written with the sweeping curiosity of a physicist who is not afraid to wander from quantum mechanics to Gödel's incompleteness theorem, from relativity to the philosophy of artificial intelligence, the book blends scientific rigor with speculative imagination. It was originally published in 1989, at a time when excitement around artificial intelligence was mounting, and Penrose's central aim was to push back against what he saw as overly simplistic claims that human thought could eventually be replicated by a digital computer. His argument, in essence, is that the human mind is not simply an algorithmic machine, but something deeper, something that depends on physical laws we do not yet fully understand, perhaps involving the as yet mysterious behavior of quantum mechanics. The story begins with Penrose positioning himself against what was then the prevailing optimism in the AI world. Many computer scientists, influenced by Alan Turing's pioneering work, believed that computers could, in principle, replicate all aspects of human intelligence if given sufficient speed and memory. This assumption was based on the Church-Turing thesis, which proposed that any well-defined computation can be simulated by a Turing machine. Turing himself, while cautious, left the door open for machines to think, suggesting in his famous imitation game, later called the Turing test, that if a computer could fool a human interrogator into believing it was human, then perhaps the distinction was moot. But Penrose was unconvinced. He admired Turing deeply yet believed that something crucial was missing from this line of thought. The mind, he argued, is not reducible to computation alone, and the attempt to claim otherwise was akin to the emperor in Hans Christian Andersen's fairy tale, parading about in non-existent clothes. The new mind being proposed by AI researchers was, to Penrose, an illusion, lacking substance. To make his case, Penrose embarks on a sweeping tour of mathematics and physics, demonstrating along the way why he believes consciousness lies beyond standard computation. His narrative does not proceed in a straight line but instead loops through diverse topics, each illuminating a different facet of the problem. He is, after all, a mathematical physicist, so he sees connections between fields that others might consider distant. Early in the book, he revisits the history of computation, explaining Turing machines with clarity and elegance. A Turing machine, he notes, is essentially an abstract device that manipulates symbols on an infinite tape according to a set of rules. Though impossibly simple, this abstract machine can emulate any algorithmic process. In practice, digital computers are just physical embodiments of this idea. They process bits, zeros and ones, executing instructions that ultimately boil down to shuffling symbols around. Yet, for Penrose, the question is not whether computers can compute things, but whether the human mind is itself a computational device. If thought is nothing more than symbol manipulation, then in principle, a computer could one day match or exceed human intellect. But Penrose points to Gödel's incompleteness theorems as evidence that human mathematical insight cannot be captured by any formal system. Gödel proved, in the 1930s, that in any sufficiently powerful formal mathematical system, there will be statements that are true but cannot be proved within that system's rules. Human mathematicians, however, can often see the truth of such statements from outside the system, using intuition and insight rather than purely mechanical rule following. For example, Penrose discusses the famous Gödel sentence, which essentially says, "This statement cannot be proved." If the system could prove it, it would contradict itself. If it cannot prove it, then it is indeed true but unprovable. A machine locked inside the formal system cannot step outside to recognize this truth. But a human mathematician can grasp it. To Penrose, this suggests that the human mind is not bounded by algorithmic limitations, that we have access to a form of understanding that goes beyond what a Turing machine could ever achieve. He knows that many philosophers and computer scientists disagree. Some argue that humans are simply fallible, and our so-called insight could itself be simulated if only we accounted for errors, heuristics, and probabilistic reasoning. Others argue that Gödel's theorem doesn't really prove anything about the human mind, it only proves something about formal systems, and human reasoning might itself be just another kind of system. Penrose acknowledges these counterarguments, but insists that they miss the heart of the matter. It is not that humans never make mistakes, of course we do, but that when we recognize the truth of a Gödelian statement, we are engaging in a kind of reasoning that transcends the algorithmic. The insight cannot be boiled down to mere symbol manipulation. Something non-computational must be at work. From this foundation, Penrose launches into a wide-ranging exploration of physics, because if the mind is not a computer, then what is it? It must, after all, obey the laws of physics. But which laws? Here he draws from his own background in general relativity and quantum mechanics. He first gives the reader a careful tour of the history of physics, revisiting Newtonian mechanics, Maxwell's equations, relativity, and quantum theory. Each step in the history of physics, he argues, represents a deeper understanding of reality, and each comes with its own paradoxes and puzzles. Newtonian mechanics was deterministic and clockwork-like, but relativity revealed that time and space are not absolute. Quantum mechanics, even more startlingly, showed that the behavior of particles is probabilistic, not deterministic. The wave function encodes probabilities, and the act of measurement collapses this wave function into a single outcome. This collapse, what is sometimes called the measurement problem, remains one of the most mysterious aspects of modern science. Penrose pays special attention to quantum mechanics because he believes it may hold the key to understanding consciousness. In standard quantum theory, physical systems evolve smoothly according to the Schrödinger equation until a measurement is made, at which point the wave function collapses abruptly into one of its possible states. But what exactly constitutes a measurement? Does consciousness itself play a role? Penrose carefully distinguishes his view from more mystical interpretations of quantum mechanics. He does not believe that consciousness causes collapse, as some have proposed. Instead, he speculates that the process of collapse might be an objective feature of reality, not dependent on observers, but triggered by something deep in the structure of spacetime itself. He has in mind what he later called objective reduction, a hypothesis that quantum superpositions might naturally collapse due to gravitational effects. While this idea was still gestating in the Emperor's new mind, he already hints that the strange interplay between quantum theory and gravity may be central to the puzzle of consciousness. The heart of his argument is that consciousness cannot be explained by classical physics or by straightforward computation. Neural networks and digital programs, no matter how sophisticated, still operate algorithmically. They shuffle symbols, process inputs, and produce outputs according to rules. But consciousness involves genuine understanding, creativity, and the ability to see truths that lie outside formal systems. This suggests that the brain must be making use of non-computational physical processes, possibly rooted in quantum mechanics. Penrose is cautious not to claim he has the full solution, but he is convinced the solution must involve going beyond the current framework of physics. To illustrate his points, Penrose brings in a delightful array of examples, metaphors, and digressions. He discusses the difference between chess-playing computers and human players. A computer like deep thought can evaluate millions of positions per second, yet it lacks the kind of deep intuition that allows a grandmaster to spot a brilliant move seemingly out of nowhere. He also explores paradoxes such as the halting problem, which shows that certain computational questions are undecidable. He draws on visual examples, like the famous Penrose triangle, to illustrate how perception and reality can diverge. Throughout, he has a knack for using concrete puzzles to highlight abstract points. One particularly charming thread in the book is his exploration of the physics of light and relativity. He revisits Einstein's insights about the speed of light as a cosmic speed limit and shows how space and time warp under extreme conditions. These discussions are not tangential, they are meant to remind the reader that our current understanding of physics is provisional, and that new revolutions may still come. Just as relativity and quantum mechanics overturned the Newtonian worldview, perhaps a new synthesis that unites consciousness, computation, and physics is waiting to be discovered. Penrose suspects that gravity, which remains the most poorly integrated of the fundamental forces in quantum theory, may be the missing piece. The way that space-time curves and interacts with quantum states could, in principle, provide the non-computational ingredient needed for consciousness. Another central point Penrose makes is about the difference between simulation and duplication. A computer can simulate the weather, but the simulation is not wet, windy, or stormy. It is just numbers representing these phenomena. Similarly, a computer might simulate the behavior of neurons, but the simulation is not itself a conscious experience. Consciousness, he argues, is not something that can be simulated in this way. It must arise from actual physical processes in the brain, processes that may involve subtle quantum effects. This distinction is crucial, because it challenges the assumption that simply building a sufficiently complex neural network or digital brain would automatically give rise to consciousness. Toward the end of the book, Penrose turns speculative, offering his vision of what future science might look like. He suggests that to truly understand consciousness, we will need a new physics that unites quantum mechanics and gravity. He admits that we are far from achieving this, but he is convinced that it is the right direction. He also acknowledges that his ideas may be wrong, but insists that the mainstream view, that consciousness is just computation, is itself deeply flawed. He would rather propose a bold hypothesis that may later be refined or corrected than settle for what he sees as an inadequate explanation. The book is not easy reading. Penrose dives into deep waters, from Hilbert spaces to entropy to relativity. But he writes with a sense of wonder, as if inviting the reader to join him on an intellectual adventure. He does not shy away from complexity, but he also peppers his narrative with humor and clarity. For instance, when explaining Gödel's theorem, he imagines a mischievous trickster writing down a statement that says, "This sentence is unprovable." He makes these abstract ideas feel almost playful, even as they carry profound implications. Throughout, Penrose is motivated by a deep respect for human consciousness. He does not see it as a trivial byproduct of neural computation, but as something extraordinary that deserves an extraordinary explanation. He is skeptical of reductionist claims that mind can be fully captured by algorithms, and he is equally skeptical of mystical claims that invoke consciousness as a magical force. Instead, he walks a middle path. Consciousness is real, physical, and lawful, but it may require new laws of physics to be fully explained. The impact of the Emperor's new mind was significant. It sparked debates across disciplines, from philosophy to physics to computer science. Some criticized Penrose for overinterpreting Gödel's theorem, arguing that it does not prove what he thinks it proves about the human mind. Others accused him of venturing too far into speculation about quantum mechanics. But many admired his courage in raising these questions, and the book inspired a generation of readers to think more deeply about the nature of mind and reality. As the book draws to a close, Penrose circles back to his central metaphor, the Emperor parading in his new clothes. Artificial intelligence enthusiasts, he suggests, are like the courtiers praising the Emperor's garments, while he insists that the garments are illusory. The mind is not a digital machine, and pretending otherwise is to be deceived by an empty show. Yet he does not deny that AI can achieve remarkable things. He acknowledges that computers will play chess better than humans, calculate faster, and perhaps even mimic aspects of conversation. But he draws a line between mimicry and genuine understanding. True consciousness, he argues, cannot be captured by algorithms. It is something more profound, tied to the deepest laws of the universe. And so the book leaves the reader with both humility and wonder. Humility, because it reminds us that we do not yet understand the mind or the universe as well as we might like to think. Wonder, because it suggests that the key to consciousness may lie in undiscovered physics, in the mysterious dance of quantum states and curved spacetime. Penrose does not claim to have solved the puzzle, but he has reframed it in a way that challenges us to think more deeply. The Emperor's new mind, he insists, is not real. But the real mind, the human mind, is more extraordinary than we have dared to imagine. And that's it. Roger Penrose's The Emperor's New Mind. Thanks for listening to Book Nibbles. If you enjoyed this bite-sized book, don't forget to subscribe for more quick, insightful summaries. See you in the next nibble.